Let's get started. Okay, so what we are going to do is that previously we learned about what is a solution. We learned about how to calculate the solubility or the concentration of a solution. Today we want to actually think a little bit deeper about the solution. So we are going to introduce some terms, the physical chemistry terms. You may have heard this one before. It is the entropy and the enthalpy terms. Okay, which is actually a very important parameters people use to describe the property of a solution. So let's actually the first things I want to introduce to you. Okay, and after we understand that concept, we want to know if today I give you two substances, I want you to actually mix them together and I want you to predict whether it's going to form a solution. Then you need to have some idea, okay, what are the things you can use to make the judgment properly. Okay, so I want to know what are the rules to predict the solubility. Okay, and then once we know how to predict whether two substances when they mix together, they are going to form solution or not, the next thing is actually we want to know what are the factors is going to affect the solubility. So basically we're going to tell you, okay, how the temperature is going to affect the solubility, how the pressure is going to affect the solubility. And then at the very end, we are going to apply all these things and summarize with one very famous equation called the Henry's law. Henry's law is just an equation, a very simple equation, tell you, okay, if you know the pressure of certain species in the air, you can predict how much of that is going to dissolve in your water solution. Okay, so that's actually one of the very last concept we want to introduce in today's lecture. So let's a quick summary of today's lecture. Then we can get back to your lecture notes. Okay, so let's talk about solution formation. So, quick questions, okay? So think about this. If today you have substance A, substance B. Okay, in order to form a solution, the first thing you do is actually what? You mix them together, right? So the first step to form a solution is actually you need to mix your solute and your solvent molecule. So first step will be your solute and your solvent. They need to mix with each other. So at current stage, you assume, okay, if you want to mix these two things together, okay, let's assume that these two substances doesn't interact for now, just for now. So one of the best example is actually if you mix two gas molecules together. Okay, for example, if today you mix, let's say your oxygens and the nitrogen together. So here, what it shows is actually inside a box, it was divided into two empty space, and then in those empty space, I fill in oxygen and nitrogen. Then I remove the blocker in between. Then what happened? They are going to mix with each other, right? So that is a solution, right? So what is our definition of solution in the very beginning of the class? Yes. So you need to mix substance, okay, in a single phase, right? So you have a homogeneous mixture of substance in single phase. Then we call it as a solution, right? So based on that definition, that is actually a gas solution, right? Your nitrogen and oxygen that mix homogeneously in one single gas phase. So that is a solution. Based on your intuitions, you know this thing will happen what? Spontaneously, right? So what does this tell you? If you have two things, okay, if they don't have specific interactions, okay, once you just mix them together, this is a spontaneous process. And then Many times you will heard these terms called the entropy. Okay, anyone know what's the definition of entropy? Randomness. So there will be actually another term we are going to go through. Okay, it's called the enthalpy. Okay, these are two different terms. So we are focusing on the entropy now. Okay, not the enthalpy. So entropy is actually the term to describe how random the situation is. And the randomness is an indication about how possible one single event could happen. So if you have a large entropy, that means you have higher likelihood to see those situations. Give you examples. Think about your room. In order to keep your room nice and clean, you need to actually put in a lot of effort, right? You need to arrange all the items, right? So under that case, the entropy is minimized, but they require you put in a lot of effort to achieve that. Under normal situations, when I say normal situation, is that you don't really pay too much attention to the cleanness of your room. What happened to your room in the end? Things will go everywhere, right? It becomes very random. So random is a lowest energy state of this, that everything is going to go to that side. So if you have higher entropy, that means actually if the situation becomes more random, it's actually a preferred state in nature. So that means actually it's going to happen spontaneously. It's going to happen naturally. Okay, so that's actually one of the very important concepts that you want to have here, because if today you just mix things together, originally each gas molecules only have a small volume they can actually participate, all the molecules they have, right? So it's kind of constrained. But if today you actually give a bigger space for them to actually run around, then they have more possible ways to actually distribute their energy. Okay, in other words, they go to a space that increase their possibility to distribute all different states they can actually have. So that's actually an increase of entropy. Okay, so make this mixing process a spontaneous process. It's going to happen naturally. All right. So that actually leads to here. Okay, so why does the mixing happens? Is because in random particle motion, okay, these two makes the configuration of particle, which is this represent the entropy, right? Okay, and then we know the larger entropy, okay, typically you will see this S, okay, is preferred. Okay, that means it's going to happen spontaneously. In other words, if you look at the next sentence, is actually mixing is a spontaneous process. Okay, so if you don't consider the interaction between your solute and solvent, you just consider the mixing process. This process is always favored process. All right. Okay, this is actually one of the very important concepts. Okay, if you are a chemistry major, this concept will go with you forever. Okay, so use this concept. Let's go through a few examples. Okay, the first example is actually if today you open a perfume bottles, what's going to happen? You start to smell the perfume, right? So what does that mean? That means actually the molecule originally was constrained within your perfume bottles. Start to do what? Diffuse out, right? It start to mix with the air. Okay, and this is a spontaneous process. Second thing is actually if you're spilling a bucket of marbles, what's going to happen? Originally the marbles were constrained within the bucket, right? you spill out, okay? Then the marbles go everywhere, right? Because you have larger space and it's actually larger entropy for the marble. Okay, it's not constrained in a little bucket anymore. This tool definitely is actually a clear example for the mixing, right? How about the third example? If today you have boys and girls, they are at their first school dance, will they actually mix well? They won't, right? Why? Because there are some extra interactions between them. Okay, so remember when I said the mixing is spontaneous, that's actually a prerequisite for that, right? That means that there's no interaction between molecules in the beginning. Okay, then we know under that conditions, the mixing is spontaneous. But under this case, okay, you know, in their first dance, they're actually repulsive. They prevent them to actually mix with each other. Okay, so under this case, we know these things probably won't happen spontaneously, but it's not because the mixing process. It's rather because there's some other interaction between the two entities. So that's actually about the mixing. Okay, the other thing is actually talking about this enthalpy term, which is actually more about the energies. All right, so in order to form a solution, okay, if you think about the things in a very molecular level, okay, the things you need to do is actually first, you have your solute. You want to mix them, that means actually first you need to actually break apart your solute. Right? So in order to actually break apart the solute, most of the time you're actually dumping energies. Okay, so that they can actually separate from each other first. Okay? So under this case, okay, assuming this is actually the final state, that is the initial state, okay, then we know the delta H of your solute, which can be calculated from the enthalpy of your final state minus the entropy of your initial state. Because in this process, you dump in the energy, so that you reach your final state, right? So if you do this, enthalpy of the final minus enthalpy of the initial, this one will be a positive number, right? Because if you know the final state has higher energy than the initial, okay? If you calculate the energy difference between the two, it should be positive, okay? So you know this typically is large M positive for ionic solute. Okay, so when I say ionic solute, the one good example is the salt, the sodium chloride. So we know salt is composed of sodium plus and chloride minus, right? And then because it's actually plus and minus, they have a very strong ionic strength between the two. So in order to form a solution, you actually bring those things apart first, and they require actually dumping energy. Okay, therefore, the delta H of your solute will be large and positive for ionic solute. So the next step is actually you also need to do the same thing for your solvent. So again, to actually bring your solvent apart large enough so that the solute can actually fill in and then eventually form the solution, okay? Under this case, using the same concept, okay, the delta H of your solvent will also be a positive value, even though it's not large, but it's still kind of breaking apart. So again, the energy, the delta H is going to be positive. So once you have separated your solute and the solvent molecules, then you mix them together. Okay, and then once you mix them together, your solute and solvent, they are going to interact with each other. And that's where you're going to see this solution to form, okay? And under this case, once you form the bonds, okay, that means actually you're going to a lower energy. Okay, you are going to form a lower energy species. So if you calculate the delta H of mixing, okay, this one is always negative, okay? If you have ionic solutions, it will be large and negative for the ionic solute solvent solution. So to summarize, to calculate the enthalpy change of your solution, it will be just the sum of the three terms. Okay, it will be delta H solute plus delta H solvent plus delta H of mixing. After combine all these effects, you're going to get your delta H of solution. So apparently, you know, if delta H mixing is the dominant term, then you're going to form the solution, right? But if today you have a dominant term of your delta H solute and delta H of solvent, that means you're going to consume a lot of energy to make the things to mix well together. So give you a quick examples. If you go to the next page. Okay, so this is actually some of the delta H solution. Okay, remember that's a delta H solution means it's actually the sum of your delta H solute, delta H solvent, and delta H mixing. Okay, all of them calculate all together for this. And then you can see here for your KOH, it is what? It is negative, right? The only term that gives you negative delta H is delta H of mixing. So under this case, you know, it's going to form the solution naturally. Okay, and then because it's negative, that means actually the heat will be released because right now you're forming a very stable solution. That's actually final product you have, right? It's low in energy. And then since it's low in energy, then all the energy that's above is going to release to your environment. Okay, so you will see the heat is going to be released to the environment and the temperature of your solution is going to increase. So on the other hand, for some other things, okay, you will see a positive value for your delta H of solution. What it means is actually you need to dumping enough energy to break apart your solute and solvent. Okay, and those terms outweigh your delta H of mixing. That's why when you calculate your delta H solution, it is positive. So that's how you should actually understand these concepts. Here is kind of like a summary, okay, about the sign of your delta H. Okay, so if your delta H solution is positive, what it really means is, you know, you're going to have strong solutes, and solvent interaction. Basically, the first two terms, the interaction break apart your solute, break apart your solvent molecules. And then they outweigh to weak solute solvent interaction. Okay, under these conditions, then you are going to have a positive delta H. Then the next question is actually if the interaction between your solute and solvent, if they are so strong, then why they bother to actually break? Okay, so what caused them to break? So eventually you have a solution, right? So the answer is actually very simple. You need to actually dumping energy to make it happen. So typically you dumping heat, okay, from the surrounding. Okay, you heat up your solution so it breaks apart. And you form the solution. Second is actually, we know mixing is actually always a preferred process. So it's actually a collective effect of both two terms that make you prepare your solution. Let's go to the other topic, solubility. Okay, we heard this term a lot, I guess, but I guess like no one actually really think about what is the real definition of the solubility, right? So today we're going to solve that puzzle. Okay, the solubility is the maximum amount of solute, okay, that can dissolve in a given solvent. Okay. So how do scientists actually determine the solubility? They do experiment, right? So what I do is actually that a given volume of solvent, I start to throw in my solute. Okay. Once I throw in, I'm going to stir. Okay. And then if it becomes transparent, okay, I know I haven't reached my maximum. I can keep throwing and keep stirring, and at some point, okay, I will find that no matter how hard I stir the solution, I will always see some precipitation at the bottom of my beakers. Okay, then I know I reached the maximum amount of solute I can dump into the solvent to form my solution. Okay, and that amount will be the solubility of less specific substance. Okay, so to visualize these things, it's more like this. Okay, assuming today you have a beaker, you fill in the beaker with water. Okay, in chapter 10 we only talk about the water solution. Then we start to throw in your solute. For example, you throw in your salt, the sodium chloride salt. So you throw in, then you will see those things go down to the bottom of the beaker, right? And then when you stir, these things start to disappear because the sodium chloride salt is going to become sodium plus and the Cl minus. And then they're going to mix well with your water molecules and become invisible. You can see I put this little S, indicates this is actually salt. It's white powder, right? Going into the water. If you don't stir, you will actually see them stay there for some time. Okay, but it will disappear. That's because this ionic salt is going to become sodium plus and chloride minus. Once that goes into the solution, you don't see it anymore. So you can keep throwing these things in, and then after some times you will see that, okay, if you after stirring, what you're going to observe is actually you're going to have many sodium plus chloride minus inside your beaker, which is invisible, but you can still see some tiny amount of the salt still at the bottom. If you keep stirring, then all the things will disappear. So what you should realize is that there are two things actually happening at the same time now. Okay, one is actually your sodium chloride salt become invisible sodium plus and chloride minus. That's actually one thing that's going to happen. But when you have actually more and more sodium plus and chloride minus exist in your solution, what's going to happen is actually it's also going to start to form the salt too. Okay, so these two will become an equilibrium process. It's a dynamic equilibrium. It means actually both directions is actually happening all the time. But in the beginning, okay, in the very beginning, because when you throw in all those solid into your water, you have maximum amount of sodium chloride. You pretty much don't have this. So because of that situation, you will actually ensure that you have maximized this process. Okay, the reaction is going to the right. But as time goes by, okay, the concentration of the sodium plus and the Cl minus is going to increase. And in the end, actually, you reach an equilibrium. That means actually the ray go to the left and the ray go to the right. They will be the same. Okay, so under that situation, we call the system reach equilibrium. So we know at certain points, okay, no matter how you stir it, okay, you will always see some remaining salt at the bottom, right? Then that's how you determine the solubility of certain species into the water. So with that concept in mind, another thing that you should know is actually, let's say, one very interesting phenomena called the supersaturated solution. We know what is solubility, right? And the solubility is actually temperature dependent. So what I really mean is actually, if today you do things at 25 degrees C, which is room temperature, and then you do the solubility test of your salt, okay, then you realize you can got, let's say, 40 grams of sodium chloride can be dissolved into your water. So imagine you do this experiment, exactly the same experiment at 100 degrees C. So now guess, you are going to actually dissolve more or dissolve less salt in into the water. So higher the temperature, okay, you're going to have more, you can actually dissolve more of the salt into the water. So now imagine this, okay. Let's say at 100 degrees C, you can dissolve 80 grams of salt. And then at 25 degrees C, you can only dissolve 40 grams of salt. If you do the things at home, okay, be careful now, okay. You're just throwing a lot of salt into your water, okay, and do the things at 100 degrees C. And then you turn off your stove. Let the temperature slowly goes down, and let it go back to room temperature. What you are going to observe is that, okay, at 100 degrees C is transparent solution, right? Because everything's actually has dissolved, okay? When it goes down to 25 degrees C, what you're going to see is still a transparent solution. And that is actually a very strange thing, right? Because you know, if you do the same thing at 25 degrees C, the maximum amount of solute you can dump in is only 40 grams. Okay, but right now, since you start from 80, when you go to 25, you should see things to precipitate out, right? But the fact is actually you won't. The solution is actually existing at a quasi-equilibrium state, okay? That means actually it doesn't know its temperature has changed that much. This is actually what you're going to see, okay? Do things at 100 degrees C, you have transparent solution. And then you cool it down to 25 degrees C. It's still transparent, you still have a single phase solution. And then, but under these conditions, we call this as a supersaturated solution because it dissolves more than it should. Okay, it's supersaturated. Okay. At this time, if you just use a toothpicker, okay, or use a chopstick, or use a fork, you just touch the beaker outside. Okay, you introduce some, you perturb the system a little bit. Okay, then what you're going to see suddenly is actually it starts to form this little thing. Okay, and it's the salt crystals is actually forming inside your solution. And then in the end, you see something like this. So under this situation, if you just pour out those solutions, okay, pour out all the liquid outside, okay, and then you measure the concentration of the salt, you actually go back to 40 grams per liter. Okay, go back to the normal situation. Okay, so that is the very typical way how people actually prepare the supersaturated solution. It is a quasi-equilibrium state. Okay, it's very interesting phenomena. Okay, if you don't know this well enough, go back home and try yourself. Next thing we're going to talk about the factors that determine the solubility if you start to mix things together. Okay, things in this chapter, we only talk about the water solution, okay? So the first concept you should know is so-called the like, dissolve, like. Specifically, okay, in this case, the things you want to actually use is actually using these two functional groups a lot. So in water solution, one of the very important concept for the water solution is that water forms the very famous hydrogen bond. So hydrogen bond is a very unique, okay, non-specific interaction between molecules. And then if you want to form a hydrogen bond, typically you will need an atom of oxygen or nitrogen. Okay, that's why I put this NH and OH here. So those are the key atoms you should look for when you see a chemical formula. So if the molecules that actually have these two specific functional groups, okay, that tend to dissolve with each other. So one quick example is actually H2O and CH3, CH2OH. Okay, what is H2O? Water. What is CH3, CH2OH? Alcohols. I know many of you can actually decipher that chemical compound, okay, quickly, okay. But from the chemical formula, at least you can see there's actually oxygen over there. Okay, so when you have this OH or NH functional group inside your chemical formula, okay, it is an indication that it can form hydrogen bond. Okay, and then that means actually both of these molecules, they are hydrophilic. Okay, anyone has a problem with hydrophilic and hydrophobic terms? Hydrophilic means actually that of water. Okay, phobic means actually hate water. Okay, so since both two molecules has this OH, right? So it means actually they are more like they are all hydrophilic molecule. They are alike, right? So based on our concept like dissolve like, so would these two molecules dissolve with each other? The answer will be yes. Second questions. Okay. Would H2O and this very long archaeal chain dissolve with each other? No. Why? There are no OH or NH in this long archaeal chain, right? Okay. So what is this archaeal chain? Okay, I guess everybody know the answer is actually no, right? So what is this? Okay, so in chemistry, okay, there's actually a course called what? Organic chemistry, right? Okay, organic chemistry is a subject that studies how to prepare all different kinds of carbon hydrogen compounds. Okay, why carbon hydrogen compounds are hydrophobic? Okay, so everybody knows the oil doesn't dissolve with water, right? Okay, what is the chemical formula of oil? It's just tons of carbon and hydrogen. So if you see a compound with a chemical formula only have carbon and hydrogen, that means it is organic compound. It is, the more you have, okay, the more carbon and hydrogen you have, okay, it's more hydrophobic. Okay, therefore it doesn't like hydrophilic molecule. Okay, like water is very hydrophilic. Okay, so in the second case, okay, you know they are not going to dissolve with each other. Okay, how about the third one? Okay, does the molecule has OH? Yes, okay, so indicates that part is hydrophilic. But if you look at this molecule, does it have a lot of carbons? What does that mean? It's hydrophobic, right? That means actually it's hydrophilic on one end, hydrophobic on the other. So what's the end result? Not completely, yes, that's the concept. Okay, so slightly. Okay, so some other factors we need to consider. Okay, if today you have the example I gave you, they are all liquid solution. Okay, so what if today you have solid liquid solution? Okay, so this part is getting a little bit more trickier. So but the rule of thumb is actually if the solid molecule is polar, then it will dissolve in water. So here we mentioned about a keyword called the polar solid. So this one will be a little bit more challenging and require a little bit more chemical knowledge. For example, this guy, what's this? Sugar. Very good. Do you know the structure? Okay, assuming you know the structure, okay, then it's very easy to answer the questions. Okay, so that is the structure. Okay. Would this substance dissolve in water? Yes, very easy, right? Yes, so many OH. It's forming the hydrogen bond like crazy. So solubility of this one in water is very, very good. Okay. Of course, this is kind of a sugar you drink. Okay, so no doubt, okay, this is going to dissolve in water. How about I2? Okay, if you have some chemical knowledge, then you know that's actually the formula will look like. Is this a polar or non-polar molecule? Non-polar, right? So this is actually non-polar, but the water is actually a very polar molecule. Therefore, they are not alike. They don't dissolve with each other. But again, this actually requires you have a better knowledge about the structure of the molecule to predict whether the things is going to dissolve with each other. So this is actually how you make the judgment, okay? Based on the chemical formulas or the structure, you can predict whether two substances is going to dissolve with each other or not. The next thing is factors that affect your solubility. So let's first talk about the temperature. So when you talk about the effect of temperature, you want to be careful because it depending on the type of solute you have. Okay, if your solute is liquid or solid, okay, when you increase the temperature, typically the solubility increase with temperature. Okay, just like the salt or like the sugar. Okay, if you go to higher temperature, you can dissolve more of it. Okay, so that's actually general rules that you should remember. Of course, sometimes you will see some substance that actually have the opposite effects. Okay, but don't worry, you won't be tested for those special cases. Okay, GEMCAN is actually testing your general trends. Okay, so all you need to remember is actually for the solid or liquid solute. Okay, increase the temperature is going to increase the solubility. However, if today what you have is a gas solute, then if you increase the temperature, the solubility is going to decrease. And I guess this is actually, you see these things all the time, right? Okay, if you have a Coke, okay, at room temperature, you can enjoy the fizzy feelings very well, right? But if you put your Coke, you heat your Coke, okay, you microwave your Coke for a minute, drink it again, you feel like the fizzy feeling is gone, right? Why? Because all the bubbles, all the CO2 originally dissolved in your Coke, they just go out. The solubility actually decreases. Okay, so it's actually very different behavior between the solid and the liquid solute at different temperature. So the things you need to memorize here is really like, okay, if today I have a solid solute, if I increase the temperature, then I should predict the solubility is going to increase. But if my solute is a gas molecule, you will show the opposite effects. All right, so the very last things that we want to go through is actually the effect of pressures. So what is the pressure going to affect the solubility? Okay, so the pressure doesn't have too much effect for the solid solute, but it has profound effects if your solute is gas. So the idea is actually very easy. Okay, so think about you actually making the soda. Okay, you're going to pump your CO2 into water. So you can think about if I exert a higher pressure of CO2, there will be more CO2 molecule goes into my water, right? So that's the general trend that you should actually remember. Okay. And then based on that concept, scientists actually find out that the amount of gas that's going to dissolve inside your water can be described by the so-called the Henry's law. Okay, so Henry's law is actually super easy. C is the solubility of your gas. K is the Henry's constant. And P is the pressure that you provide. Okay, so P is the external pressure you provide on the solution. So it follows a linear relationship. So from your textbook, you can actually find all the Henry's constant for all different gases. If you're going to be tested for this concept, most likely this is actually going to be provided. And then the question you're going to encounter is like this, okay? What pressure of CO2 is required to keep the concentration of CO2 in a bottle of root beers at 0.13 m? So once you see this type of questions, okay, then you should ring a bell that, okay, apparently this is talking about the effect of pressure on the solubility in aqueous solutions, right? And you should definitely go to the Henry's law constant or Henry's law's equation, which is C equals to K times P. So right now, you know the concentration is actually 0.13. K, okay, you know it's CO2, right? So I'm going to go back to this table. Check out the K. K is 2.3 times 10 to the negative 2. And then you want to find out what the pressure you need to actually exert on the solution. Okay, so key is what? The key is actually, can you actually recognize these questions is testing your understanding about the effect of pressure on the solubility of gas in a water solution. If you know that, then you know there's actually only equation you can use, which is actually Henry's law equation, right? And then all you need to do is actually plug in the information you got from the questions and solve for the unknowns. All right, so that's it for today's lectures.